pipette configuration for a 3 decibel attenuator. Calculate the Y parameters for this 2-port system where we have to identify, in fact calculate Y11, Y12, Y21, Y22. And remember, these are the admittance parameters. And those of you who are not aware of what admittance is, it's just simply a reciprocal of impedance. Our problem 1 was based on impedance, if you recall, so that should help you. Now, those of you who are not familiar with what pad configuration is, on the top right corner of your screen, what you see is a pipette attenuator. And it's so called because it's basically a layout and design resembles to that of the Greek letter pi, right? It makes a pi, meaning that it has one series resistor and then the 2 parallel shunt resistors connected to the ground at the input and the output. So here's the input and there's the output right here. They're most commonly used in radio frequency and microwave transmission lines and can be balanced or unbalanced design. This one in particular is the balanced with the equal impedances. So let's try to figure out how we can solve for these admittance parameters. First thing I want to do is I want to label our circuit right here. Okay, so say this is going to be this is in, this is out right here. Okay, this is say V1 and here we have V2, correct? Say here this is I1, this is going to be say I2 here. In fact, you know, I can say this is my I2 here. This is my I3. This right here is I3, and this here is I4, and this here is basically my I5 here, correct? And say this is my node 1, this is my node 2. We are going to apply KCL at these node 1 and node 2. So again, V1, V2, I1 is the current going into the input port. This is I2 going into node 2. We have I3 here, and then I4 and I5. And also I'll just label the resistors as well. This is going to be R1, say. This is going to be R2, which is 18 ohms. This is 300 ohms. And then R3 over here, which is also 300 ohm. Okay, let's apply KCL at node 1. Okay, node 1. If you look at the current that's going into node 1 is I1, correct? I1. And so what is the KCL states? Current entering the node equals current leaving the node. So current entering is I1, current leaving is I3 and I4, correct? I3 and I4. Let's look at what is I3 here. I3 is the current going through R2, which is basically, if you look at, you got V1 here, which means the voltage at this node is also V1. You have V2 here, which means the voltage over here is also V2. The direction of the current is going from node 1 to node 2, which means V1 has a higher potential versus V2. Therefore, the voltage across R2 is V1 minus V2 over R2. So let's put it down over here. I3 equals to V1 minus V2 over R2. I'm going to put it in an expression format, and then I will plug in the values, plus I4. I4 is just simply the current that is flowing across this R1. You know the potential here is 0 volt because it's connected to ground, correct? So just simply V1 over R1. So V1 over R1, and if we plug in the values, so this becomes V1 over R2 is 18 plus V1 over R1, which is R1 is 300, minus V2 over R2, R2 is 18, correct? Which would mean my I1 equals to, if I add the two coefficients, 1 over 18 plus 1 over 300, let's see what do we get here. 1 over 18 plus 1 over 300, correct? We get 0.0588. I'm just gonna round it off and write it down. 0.059 V1 minus V2 over 18. So 1 over 18 is, that gives me 0.055. So I'll just round it off again. Minus 0.056 V2. And I'll say this is my, equation 1 here. Let's now try to apply KCL at node 2. At node 2. So let's look at the circuit again here. This is our node 2, right? We have current entering this node, which is I2. We have current leaving this node, which is I5. And then we also have current entering here this node, which is I3. So the current entering the node are I3 and I2. Leaving is I5, right? Hence the equation becomes I2 plus I3 equals to I5. I'm sorry, I did not realize that I was not recording and I just kept on writing. So this equation right here can also be written as I2 equals to I5 minus I3, correct? Because remember, this is what we are striving for. We need to get equation for I1, which we already have. Now we're getting for I2. I5 is simply the current flowing in this part of the network across R3. Because we have V2 here, that means the voltage across this node is V2. V2 over R3 is going to give us I5, right? And hence, I have I5 written as V2 over R3. I3, we did it earlier, and that was V1 minus V2 over R2. So I simply have V1 minus V2 over R2. I'm going to further expand this equation and write it down as V2 over R3, negative become plus V2 over R2 minus V1 over R2. I can further simplify or rewrite this equation as negative V1 over R2. R2 is 18 ohms. Remember, R2 is 18 and R3 is 300, correct? Plus V2 over R3. V2 over R3 is 300 and V2 over R2 is 18. Now we're gonna look at the coefficients. 1 over 18 is going to give you 0.056, negative sign here, so you have a negative sign here. And 1 over 300 plus 1 over 18, since V2 is common to both the terms, if we do the math, we get 0.059 V2. And I label that equation as equation 2. So I have two equations, equation 2, equation 1. And we look at the coefficients of V1 and V2 parameters, right? In a matrix form, these equations can also be written as like you see in brown. I1, I2 equals to Y11, Y12, Y21, Y22 times V1 over V2, right? If you expand this, it can be transformed into something like this. But here we are going from this equation in a matrix form. And all we need to do here, so the answer is in green, I1, I2, Y11 is basically this right here, Y12 is this right here, Y21 and Y22 times V1, V2. Hence, our admittance parameters are these over here, and that's what we were looking for.